Hi, welcome to episode 2 of Adventures in Common Lisp, where we are going through Peter Norvig's classic Lisp text, Paradigms of Artificial Intelligence Programming. If you'd like to learn a little bit more about what this series is about, please watch episode 1. For now, let's get right to the exercise. Today we're looking at exercise 1.2. Write a function to exponentiate or raise a number to an integer power. For example, power 3/2 equals 3 squared equals 9. Before we begin, let's recall the definition of exponentiation. When we raise a number to an integer power, all we're doing is multiplying that number times itself some number of times. For example, 2 to the 1, well, that equals 2. 2 squared, 2 to the 2 equals 2 times 2. 2 to the 3 equals 2 times 2 times 2, and so on. And by definition, because it makes a number of laws easier and more straightforward and more regular, we say that any number to the power of 0 by definition equals 1. So, as it says in the problem, we're going to be defining a function called power, which is going to take 2 arguments. We'll call them n and m. There's our doc string that tells us what this function does. And now we think about how we need to approach this problem. If we were solving this problem in a programming language like C or JavaScript, our first intuition might be to write some kind of for loop where we iterate m times and multiply n times itself that many times, keeping track of our calculation in some kind of temporary variable. You can do this in Lisp. Lisp is a multi-paradigm programming language. It's designed so that you can express the solution to your problem in whatever way is most natural to you. It doesn't restrict us in any way compared to a programming language like Haskell, for example, which heavily discourages any sort of mutation. We can do that in Lisp. That being said, it is somewhat better style in Lisp to sort of avoid iteration and mutation unless it really is the thing that makes the most sense. Lisp is really geared towards functional programming in a way. It's considered, I suppose, good Lisp style to program functionally. So, can we solve this problem functionally? Well, this is a mathematical problem, and mathematical problems do really lend themselves well to recursion. In particular, any problem which involves natural numbers, we can often use a strategy which is called structural recursion. Structural recursion isn't limited to natural numbers. Um, any any sort of recursively structured data, lists and trees and so on, the problems involving them can often be solved using structural recursion. Um, so what do I mean when I say that natural numbers have a sort of recursive structural property? Well, one way you can think about the natural numbers is a natural number is either 0 or it is the successor to some other natural number. So you see how that's sort of a recursive definition. We build the complete infinite set of natural numbers by constantly building on the numbers we've built before. And with this definition, we have sort of a pattern, a way of thinking about how we're going to solve this problem. We'll use a con statement, which is kind of like an if statement or a case statement. And we'll start with our base case where m equals 0. And well, we know by definition that equals 1. Otherwise, and we write otherwise in Lisp as true because con statements are evaluated from top to bottom. They stop whenever they encounter an expression which is true. So here we want it to stop if it ever gets down there. So we just write t for true. Well, this is our successor case here. So we know we want to do something recursively with m minus 1. Because that's the variable we're performing this sort of structural recursion on. And how do we calculate n to the m, given that we've already computed n to the m minus 1? Well, easy. We just multiply it by n one more time. If you want to see the math justifying that, just remember that any number to the power of a times any number to the power of b equals n to the power of a plus b. That's a fundamental law of exponentiation. So, of course, n to the 1, which equals n, times n to the m minus 1, well, that just equals n to the 1 plus m minus 1, which just equals m. So there we go. We seem to have solved this problem. Let's just compile it and make sure that this does what we want. Let's compute 2 to the 8. 256. That's correct. It looks good based on this quick ad hoc testing. If you're familiar with mathematics, incidentally, this is very similar to how proofs by induction work, where you prove something for a base case and then assume it's true for n and prove it for n plus 1. That assumption of n plus 1 being true if n is true, combined with the fact that 0 is true, means that suddenly you get everything. If you have 0 and n plus 1 is true, then 0 plus 1 is true, then you have 1, and so on, all the way up to infinity. The only thing that's worth mentioning is that the book actually provides its own solution to this exercise, which looks a little bit different from what I've written. And that's because this solution is very inefficient. Now, in practice, this probably won't really matter. You're not going to ever be writing your own power function. There's one built into Common Lisp. And realistically, it's unlikely you're going to be dealing with... Oh, look at that. I did get a Stack Overflow. Let's just quit out of there. So you can see that there is a problem with really, really large numbers. I mean, this is an enormous number, and it gets through okay and is computed instantly. But there is a more efficient way of solving this power problem that's fun to think about. If you look at this, every time we do this recursion, we're just subtracting 1 from m, which means that we're going to run this function m times, roughly. So the amount of time it's going to take to execute is going to grow linearly with m. As m increases, the runtime will increase proportionately. And we can do better than that. And to do better than that, we just need to take advantage of some more nice properties of exponentiation. N2, now this is true in general, not just for 2, but n to the power of 2m equals n to the power of 2 to the power of m. And you'll just have to believe me that this is true. If you'd like, you can prove it yourself. I believe you can probably do that, in fact, using induction. But that's outside the scope of this video. So how does that help us? Well, what we're going to do is we're going to split this case in two. We're going to use the even p function. The p there means predicate, which means that this is a test on m. It's going to test m and return true if it's even. And let's actually fill that out in a second. This in the t case, that's the odd case because any number is either even or odd, or any integer is either even or odd. But there's no point in writing this because it's already implied, so why waste time doing the test? So in this case, unfortunately, there's nothing much we can do. We're just going to do what we were doing before. Let's close that all the way up. But in the even case, we've got a little bit of an advantage because rather than computing 2 to the m, we know that m is some kind of even number. So therefore, m actually equals 2 to the power of some other number, m prime. Or sorry, not 2 to the power of. M actually equals 2 multiplied by some other number, m prime. That means that what we're actually computing here is n to the power of 2 times m prime, which, if you'll recall, equals n squared to the power of m prime. So what this means is that when we do this, we can actually just outright half the number of computations that we need to perform. So what I'm going to do is I'm going to store m divided by 2, which is, that is m prime, of course. You can see that easily by just rearranging this equation. But I'm going to store that in a variable. And to be perfectly clear here, m/2 is a variable name. It's not a computation. The computation is done here and then stored in m divided by 2. It's just, this might be a little bit unexpected if you come from some other programming languages which have infix arithmetic. This really does look like a computation, but because Lisp doesn't, it lets you be very flexible with how you name things. So this is a valid variable name, and it's what I'm going to call the variable which is storing the result of that computation. So let's get m prime, m over 2, and let's compute well, what do we want to put in here? We want to put n squared. And this won't actually work. It will cause an infinite loop because you'll if you call power with n2 right now, what's going to happen is it's going to come here and it's going to end up trying to recompute that. So a nice easy way to solve that is, well, we know that n squared is just n times n. So yeah, there we go. That actually should do it. Let's find out. So I compile it, and it seems to work. And let me just sort of talk through why this is so much faster. Consider the case of, well, I use 2 too much. Let's say n to the 100. So in the previous version of this function, as I already argued, this is going to recursively call power 100 times. One for each time we have to multiply n by itself. With this version, however, the first time through we're going to see that m, 100, is even. So we're going to compute m divided by 2, which is 50. And instead of computing n to the power of 100, we're going to compute n times n to the power of 50. And then we're going to recursively call ourselves again. And we're going to see that we're going to, 50 is even, so we're going to actually end up just computing, well, this has already been computed, but n times n times n times n to the power of 25. So as you can see, every time this m here is shrinking quite rapidly. We're going to get, the next time through 25 is odd, so we're going to be down to 24, but then we go down to 12, and then down to 6, and then down to 3, and then down to 2, 1, and then 0. So that's so many fewer times that we have to recursively call ourselves. This is, I mean, I can count this. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times rather than 100 times. So whenever you have a case where you're dividing the number of times you need to compute, each time you sort of recursively simplify the problem, that's what's called logarithmic time. Because if you look at the runtime, it grows logarithmically, like a logarithmic function if you graph it out. And that is so much faster. I wonder, will we be able to compute this? I'd be surprised if we couldn't, actually. So it takes a little while, but we haven't hit a Stack Overflow yet. I'm sitting here on pins and needles. Is that the expression? On the edge of my seat. Well, I suppose if it's taken this long, well, at any rate. At any rate, that is a better solution to exercise 1.2. I'll let you know in the next video if it finishes. For now, good night. Thanks for watching. I will see you again next time for more adventures in Common Lisp. Please like, comment, or subscribe if you enjoyed this video at all. If you have any questions, please leave them in the comments. I'll be happy to answer them to the best of my abilities. Take care.